Hello everyone, I'm Mr. McBrien. This is SCH3U, Empirical and Molecular Formulae. So in the Ontario curriculum, objective D2.4 is that students will determine the empirical formula and molecular formulae of various chemical compounds given molecular masses, molar masses, and percentage composition or mass data. This is what we're going to work on today. So the basic concept is this. If we have a percent of various elements in a given compound, we can, through various means of calculation, come up with a molecular formula. So our objectives today. We're going to introduce the concept of structure elucidation, talk about elemental analysis, something slightly different than that, work on converting weight percent to number percent or molar ratios, and then tackle the problem of combustion analysis results defining empirical formula and use the empirical formula to get the molecular formula. Okay, so let's talk for a few seconds about structure elucidation. It's a very different problem today than it was 25 years ago. The basic problem is figuring out what compounds are contained in a given sample. A flower, a beetle, a fragrance, a leaf. Typically they're natural products like this that are elucidated. And identification of these organic molecules has been a really interesting puzzle. A very fun problem to try to figure out what a given pigment might be, or some kind of active compound maybe in an herbal remedy. It's one of the more interesting puzzles in science. However, this puzzle is becoming easier and easier. And the reason for this, of course, is technology. Nowadays, we have ready access to accurate mass spectrometry and even multidimensional techniques, MSMS. Particularly important is high-resolution nuclear magnetic resonance, NMR. And nowadays, there are software programs such as ACD Structure Elucidator that allow for automated data interpretation once we do have these data. So a little prediction on my part, whereas today elucidation still has many manual components other than for certain easy problems, really within the next 20 years we can expect that this problem will be completely automated. Quick look at some of the techniques that make this possible. So NMR instruments today are extremely powerful and sophisticated and of course expensive. And right here close to home we have mass spec instrumentation being manufactured by organizations such as AB-SciX. Okay, quick note about the carbon-hydrogen analyzer. This is discussed in your textbook. I think it's important to note that today elemental analysis is not routinely done in this manner. We can still get some value out of looking at this. It'll give us a better understanding of the ratios of elements in a compound. It'll illustrate the difference between empirical and molecular formulae, and just give us an idea of what was done in the past. So this is a look at a combustion analysis widget. So the schematic gives us the idea that we push oxygen in to obviously allow for the combustion, introduce our sample, and then what we do is absorb the water and the carbon dioxide and measure the amount of this coming out. So obviously it's not a very sophisticated technique. So other elements won't be absorbed and have to be accounted for in other ways. Okay, so let's back up a little bit and talk about some of the concepts that make the combustion analysis technique possible. So you might remember we've talked about this problem before. The question of what percentage of these fruit is grapes. And the answer isn't the same if we consider the weight percent versus number percent. And today we're going to consider both. We're going to consider the weight percent and also the ratio of moles, which amounts to the number percent. And we'll achieve this by using the mass percent of, well, we can still keep our fruit metaphor here, the mass percent of oranges and grapes in a bucket of fruit. But if we know the average weight of an orange and the average weight of a grape, then we can determine the number percent rather than counting all the fruit. Okay, and where are we headed with that? We're headed towards this idea of the simplest whole number ratio of given things. And of course, we're not going to continue talking about oranges and grapes. We'll talk about the atoms in a chemical. So this is an important definition. The empirical formula is the simplest whole number ratio of atoms in a given chemical. Okay, so some examples. If we take hydrogen peroxide, the formula is H2O2. Obviously, this isn't the simplest ratio. 2 to 2 can be simplified to 1 to 1, or OH. So our molecular formula is H2O2. Our empirical formula is OH. Benzene, same idea here. C6H6 can be simplified to CH. So our molecular formula is C6H6. Our empirical formula, CH. Ethylene, again, it's trivial to see that we can divide both by 2 and get an empirical formula of CH2. Now on the other hand, propane, C3H8, the molecular formula can't be simplified, and so the molecular formula and the empirical formula are the same, C3H8. So once we have a molecular formula, we can figure out percentage composition. And usually when we talk about percentage composition, we're talking about weight percent, and so we have to do a certain number of operations before we can determine that number. But with our knowledge of molar mass of elements, this is not a particularly difficult problem. Okay, so glucose. The molecular formula is C6H12O6. What's the empirical formula, and what's the percentage composition of glucose? Well, the empirical formula again is the smallest whole number ratio of the elements, and we can see that there's a common number across these, 6. And so if we divide each one of these coefficients by 6, we get CH2O is our empirical formula. Now once we have this empirical formula, we can calculate the percentage composition. So that's the percent of the element by mass, being the mass of the element times 100% over the mass of the compound. Pretty straightforward. We can use the formula to get the percent composition. So our total mass, now we could, if we wanted to, use the molecular formula, but the math's a little easier if we use the empirical formula. Total mass of the empirical formula, sometimes we simplify down this down to MEF, is 12.01 plus 2.02 plus 16. So the mass of the empirical formula is about 30 grams per mole. So then we can get our percent carbon in the molecule by simply dividing the mass of the carbon element, 12.01, by the total mass times 100% gives us about 40% carbon in the compound. Similarly, we can find the percent hydrogen to be 6.73%, And we can see that glucose is in fact 53.28% oxygen. Pretty straightforward exercise, really. So what about saccharin? We can do the same problem with saccharin, C7H5NO3S. We want to find its empirical formula and the percentage composition. Well, the empirical formula is pretty trivial in this case. Because the coefficient for nitrogen and sulfur are both 1, we know we can't simplify that any further, so the empirical formula is the same as the molecular formula. And we can go through and find the percentage composition by first getting the molar mass, 183.19. And our percent carbon is just take the coefficient, 7 times the molar mass of carbon, divided by 183.19 times 100%, it's about 46% carbon. Percent hydrogen, again, take the coefficient. There's 5 hydrogen atoms in each saccharin atom, saccharin compound, and so it's about 2.75% hydrogen, 7.64% nitrogen, and so on. Okay, so we just saw how to get the percent composition from the empirical formula, but we can work in the opposite direction as well. And then once we can do that, we can get the molecular formula from the empirical formula. In other words, we can work in the opposite direction that we just did. And it might be helpful to take this in flowchart form. So we can take our mass percents for a given compound, use the molar mass for each element to find the number of moles of each element. Then we can find the molar ratios, a trivial problem, and then assign our subscripts by simply converting to whole numbers. So this is really pretty simple, but it's useful to go through this a few examples in order to illustrate this idea. And we're going to do that next. So for our first example, our compound was run through the analysis to get 82.67% carbon, 17.33% hydrogen by mass. And our problem is to find the empirical formula for the compound. So what do we do first? We need to move ourselves into a gram kind of consideration rather than percent. So what we can do is just simply say, let's assume we started with 100 grams of sample. Then if it's 82.67% carbon, then we can say that 82.67 grams would have been carbon. And if it's 17.33% hydrogen, then 17.33 grams are hydrogen. This is just a convenient way to work. It's somewhat arbitrary us taking 100 grams, but of course the math is very simple. So we can convert those masses to moles very easily. We've been doing this now for over a week. 82.67 grams of carbon times a mole of carbon for every 12.011 grams gives us 6.881 moles of carbon. Similarly, we get 17.19 grams, 17.19 moles of hydrogen. And so what's next? We have our number of moles. Now we need to find the molar ratio. And of course we learned in grade 7 math, that we divide by the smallest number to get the ratio. So 6.881 is the smallest number, so 6.881 over 6.881, we get 1, of course, and that'll always be the case for our smallest, for our least prevalent element. 17.19 over 6.881 gives us almost exactly 2.5. What does this mean? This means that we have 2.5 hydrogens for every 1 carbon. But is this our empirical formula? No, of course not, because it's not a whole number ratio. So we have to put a little thought into this and see that if we multiply both numbers by 2, we will get 2 carbons for every 5 hydrogens, or C2H5 is our empirical formula. Now, as we discussed earlier, we can get the molecular formula from the molar mass once we have our empirical formula. So if our empirical formula is C2H5 and our formula weight is 29 grams per mole, we can simply compare this to the molecular weight. So this is the formula weight for the empirical formula. We can compare this to the molecular weight for our compound, which might be determined by other means. So if our molecular weight is, or our molar mass for the compound is 58 grams, and our formula weight for our empirical formula is 29, it's pretty easy. We can do by examination. We can see that the molecule is actually twice as heavy as the empirical formula. And so we can multiply through by 2 and get the molecular formula being twice as large as the empirical formula. Multiply both coefficients by 2, C2 becomes C4, H5 becomes H10, and we get our molecular formula. So with a pretty quick, pretty easy to follow operation, we went from percent of a given element and a molecular weight, or a molar mass. We went from those 2 pieces of information to a molecular formula. Okay, so now in the classroom we're going to stop and do problems 1 to 3 on the worksheet. I'd invite you to pause the movie and do that as well at home. Okay, welcome back. Now let's talk about combustion analysis again for a second. We already discussed that combustion analysis is a rather outdated technique, but it can be used to determine the empirical formulae. What we do is we take a weight amount of the compound, burn it in oxygen, and one way or another analyze the products. So a GC can give us the amount of our given products, or other absorbers can be used. And this is a very effective technique for hydrocarbons. So another simple flow chart: we weigh our sample, we burn it, and weigh the CO2 and H2O that comes off. We can use those things to calculate the number of moles of carbon and the moles of hydrogen that were in the original compound, because remember, we only put in oxygen when we burned it, so all of the carbon in the CO2 had to come from the compound, and all the hydrogen in the water had to come from the compound. We can calculate again the molar ratios, and then from there we can get the empirical formula. So it's just one additional step beyond the percent composition case. Okay, so a definition just for completeness sake: combustion analysis is the technique of finding the mass composition of an unknown sample by examining the products of its combustion. And our general case, and we're going to have this equation up a few times to illustrate the points here: X plus lots of oxygen gives us CO2 and H2O. And notice this is not a balanced equation. So an example, we could burn 0.25 grams of a given compound and get 0.686 grams of CO2 and 0.562 grams of H2O. Okay, so this is interesting. We started with 0.25 grams and we wound up with well over 1.2 grams by my calculation. So where did the extra mass come from? Yes, that's right. All the oxygen that we put in is the additional weight that we see there. Okay. So our challenge is to find, from the masses of the CO2 and the H2O, find the mass of C and H that must have been present originally in the compound. And we can just use the percent composition in CO2 to get that answer, right? So we take 0.686 grams of CO2 that we collected times the percent composition of carbon in CO2, which is 12.01 over 44.01, equals 0.187 grams of carbon. Similarly, the hydrogen is 0.562 grams, the amount of water we collected, times, and notice the coefficient 2 here. This is because there are 2 hydrogens in each water molecule. So the percent hydrogen in water is just over 2 grams for every 18 or 1 in 9. At any rate, we get 0.063 grams of hydrogen. Now there's a really easy check for us to do here, right? We started with 0.25 grams of material and we burned it, and we said that 0.187 grams of that material must have been carbon, 0.063 grams must have been hydrogen. If we add these together, we get 0.250 grams, right? So this indicates that our material was 100% carbon and hydrogen. There are only carbon and hydrogen, there are no other elements. Now, if we get some number much higher than 0.25 grams, we know we've made a mistake and we need to go back and do a check. And the most typical mistake that students make is forgetting that 2 right there. Okay, so now we have our 0.25 grams of material. We know that compound X must contain only carbon and hydrogen because that's all of the material we started with was 2.25 grams. We can find the number of moles of carbon and hydrogen in the original compound, and we do this the same way we've done it before. We say we've got 0.187 grams of material times 1 mole of carbon for every 12.01 grams gives us 0.0156 moles of carbon. And the hydrogen case, we get 0.063 moles of hydrogen. So next, we can find the relative number, the molar ratio between carbon and hydrogen. We just divide by the smallest number of moles, which of course was 0.0156. So what do we get? We get 1 carbon for every 4 hydrogens. And of course, if we got fractions, we'd have to go through and multiply through by a whole number to get a whole number ratio to put into our formula. But in our case, we have 1 to 4. So CH4 is our empirical formula. Okay, so to summarize what we do for combustion analysis, we find the mass of carbon and hydrogen that was present in the sample, find the actual number of moles of carbon and hydrogen in the sample, find the relative number of moles, the molar ratio between carbon and hydrogen, convert it to whole numbers if necessary, and then write the empirical formula for the unknown compound. A few notes on this. You want to always do a quick check to make sure that the mass of C and H adds up to the total mass combusted. If it's higher, you've made some kind of mistake. If it's less, the remainder is an unknown element. There's lots of other elements besides carbon and hydrogen that could be in our compound. Usually, in questions at the undergraduate level, if there are any other compounds present, you'll be told what they are. Nitrogen and oxygen are the usual culprits. And you can just use simple subtraction to find out how much there is of the other compound. So this gives us the empirical formula. We already talked briefly about using that empirical formula plus the molar mass to get the molecular formula. Pretty straightforward. We calculate the empirical formula mass, sometimes abbreviated as MEF. Find the number of formula units in the overall molecule by dividing, and then just simply multiply through. And we already did one, but we can do another one here. The molar mass of glucose is 180 grams per mole, and its empirical formula is SCH3U. Figure out the molecular formula. So we take the empirical formula and calculate the mass, in this case 30 grams. We find the number of formula units in the molecule by division. We can see 180 over 30 is about 6. And then all we have to do is just multiply the coefficients for all of the elements by that whole number. So CH2O becomes C6H12O6. Don't forget to multiply through all of them. Okay, so in class we're going to start work on worksheet 4, questions 4 and 5. If you're working through at home, feel free to do that as well. Okay, lots of homework today. Please complete that molecular formula worksheet. Read through the textbook sections 6.2 to 6.4. Don't forget the labs are due tomorrow. And if you have the time, start the empirical formula homework sheet as well that has some more combustion analysis problems. So today we considered the problem of structure elucidation, determining elemental composition for unknown compounds, defined empirical and molecular formulae, talked about combustion analysis in the carbon-hydrogen analyzer, and worked on determining the molecular formula from percent composition. Thanks very much for listening.